This is the third lecture for chapters 7 through 9, and we'll start this off looking at just, again, how species R versus K selected species kind of vary. We'll do a couple, or have a couple looks at some of these lines, in particular with a cemetery lab that we'll do, which is kind of interesting. Looking at how these curves lay out here, you should kind of know what they sort of mean. And if I'm not mistaken, we'll check myself on this later, this top line here is what we refer to as a type 1 species. Type 2 is right here in the middle. And a type 3, again, if I'm not mistaken, I may have the 1 and 3 mixed up, but I think I'm right. The idea of it's more important. Looking at these three different types of species, type 1s, like the rhino here, notice as far as the percentage of the ones that make it. So we're kind of pointing up here at the top. Most rhinos survive birth and early age because of a lot of support from the parents. So they kind of mostly will survive, and they make it to whatever age in life, and then eventually at some point they have an expected lifespan, whatever it happens to be, and then they all fall off kind of at the end, which is quite different from, say, example like our salmon. Salmon will produce hundreds, if not thousands of offspring, and really with the understanding that most of them don't make it. So you can see the percentage of ones that are born, most of them die off really, really fast. Insects, smaller things tend to do this. And then once they kind of get past a certain age point, they tend to continue surviving, and then they make it to whatever their expected life period is. There are other species that really there's no rhyme or reason. Birds is a good example. Squirrels are another. That they are born and then they just kind of get picked off along the way equally, and there's no rhyme or reason. So they just kind of go through the lives. But a big difference between like 1s and 3s. This is going back into the idea of pressures on species. Some conditions will allow a species to excel and do well in its environment. This is the biotic potential we have in here. So if you have a lot of food available and other resources that species tend to like, you will see them being very successful, and they will go through exponential growth as they're going up here. But eventually, everything has some type of resistance, and these are the environmental resistance factors. And these things will push down and prevent a species from getting out of control. If you are a K-selected species, these are more impactful on a species because they do everything more slowly. And these will help keep the populations in check. So left alone, humans are not involved. Typically, if you go into a location and you're looking at cougars, if they're naturally in a location, you may have a certain number, let's just call it 10, in 100 square miles. And you come back in 10 years, it's still 10 in 100 square miles, because this is what the population, the location will support. All right, moving along. This is a little bit of math, just looking at some changes in population growth. Here we go. You got some population where there's 100 individuals, and then eventually someday they go up to 105. Okay, so what is the growth? What is doubling time? Well, to figure this out, we're going to look at the change from 100 to 105. Okay, that's 5. In comparison to, as far as a growth rate, what they would have would be 5%. So what is the population growth rate? So 5 divided by 100 times 100% would give you 5. For doubling time, there's this thing called the rule of 70. And all you're doing there is you're taking 70 and dividing it by whatever your growth rate is as a percentage. So you may be given a decimal, and we'll talk about that more in a slide or two. And then whatever that turns out to be, in this case, of course, it's 14 years, that is going to be your growth rate. And then you have this, which is kind of saying the same thing. We're not going to really focus on that too much. Here we go. So we have this equation, and you may have used this like in econ or something like that. this equation, and we'll talk about this and I'll go through the math on it in just a second. So this is what all those factors mean. And again, what you're really looking at here is you have some original population, you have what it is after a period of time, and then E is just that button on your calculator, natural log, inverse natural log, and then just looking at the growth rates and the time that it goes through. So for example, if you had some bunnies, you got 10, and it has an exponential growth rate of 0.5, and again, that is 50% times 100. The growth rate, how many bunnies would you therefore have in 1 year, 5 years, and 10 years? In your calculator, what you would do is put 10 in for the original number. Then you would press the E button. So find natural log, it's probably inverse natural log. And then the growth rate would be 0.5. And then it's just 1 year, if you're doing 1 year. And then see what number pops out. If you did that, you should. Oh, let me get out of the drawing mode. These are the numbers you would get for all those calculations. So we'll do that in class. Just to kind of breeze over what we're kind of doing there in this little calculation is it doesn't matter what the number is. There's this rule of 70, and I think I might have this on the next slide. So let me actually bounce over there and see if I do. I don't, but I'm going to write over you. Okay, so I'm going to start drawing on this page that little equation that we got going on over there. This is the value that I would have if I have twice this original population. So that's the whole NO-NT thing. And then I've got E to the RT. Now just looking at the math of this, I can cancel out a couple of units. I can get rid of the X, and then I'm just left with 2. So I have 2 is equal to ERT. That's not too bad. And now if I take the natural log of both sides, what you'll find is you get 0.69, kind of close to 70, is equal to RT. So the rate times the time. Now if I want to know how long is the doubling time, I can divide both sides by, R, that's an R. Divide both sides times R, and that is the percentage. So I'm going to switch these. Normally it would be like 0.5. Let's say it's 5% growth rate. So that's 0.05. So I'm not going to use 0.05. I'm going to multiply it times 100 and the top by 100. And you get 69, but for whatever reason we use 70 divided by not 0.05, but 5. And that is going to be equal to whatever the time was. And we did this example on the previous slide, and it was 14. So that's kind of how the math works out. Now looking at as far as how populations change, the moose on Isle Royale, they do go through this population rise and crash if they don't have predators able to control them, like the wolves, because they act more like an R-selected species. This happens to be a reindeer. An R-selected species as compared to something which is maybe a little larger. So they will have their populations explode, as you see on here, but then eventually they will come back down to whatever the carrying capacity is. Usually they fall below. Okay, a couple of comparisons. They kind of sound the same, but they're a little different. Population size is just the number you have in a particular location. Density is per, for example, square mile or square kilometer. So it takes that population size and defines it within a set parameter unit of 1, you could say. Or you could say like 10 square miles or 100 square miles, but something defined as. A comparison in the United States, you could say, what is the population of, say, Wyoming? It's a certain number there. What is the population density would be the number per square mile. Looking at that density number, you could realize that, oh, well, Wyoming is kind of sparsely populated with humans. Okay, new idea. Again, moving away from that last one. Predator-prey, the best example of this is on Isle Royale, where you have the moose and the wolves. That's a huge conversation we can get into in class. It's really good. And we see this delayed effect with the interaction between species. You have the predator, in this particular case, the lynx, which is lagging behind. And again, if we kind of focus on this part right here, circle that in. It's a little bit delayed there, kind of appropriate. You have the hare population, and then which explodes first, and then because of that high population, the lynx responds and its population goes up accordingly, following along with the hare. But then of course it runs out of hares to eat, and then its population crashes too. And this process just keeps repeating itself over and over again. So this is a pretty typical relationship between a prey and a predator. But again, the wolves in Isle Royale and the moose kind of do something very similar to that. All right, good place to pause.